Hey, my name is MrCaproni, and I'm an AP statistics teacher at Western Hills University High School. Today, we are going to be continuing a long conversation we've been having about confidence intervals and hypothesis testing. In particular, today we're going to cover the last one, which is the two-sample t-test. Now, we've covered a bunch before this, so if you're feeling lost or confused or like you just haven't seen all the videos, you can always check out my YouTube channel at MrCaproni, no space, no period, and you can see any video where we've covered all the content before this and any video I post after this. So feel free to jump on there and catch yourself up. With that said, I hope you guys can learn something new today because we're jumping into day 23 of AP Stats. So we're continuing on with chapter 23, which is about comparing means using this two-sample t-interval or t-test. Now, as we move along, you're going to realize there's a lot of similarities between what we've done in the past and what we're looking at today. Now, starting off, remember, this is quantitative data. So that means that we're dealing with data where we're able to have the mean and standard deviation of that data. This has nothing to do with proportions. So once you have a list of data, you're able to find the mean, you can find the standard deviation of that. And in this case, you can see they actually have a display of a box and whisker side by side, box and whisker plots, so that they can compare to two different things. Notice down here it says brand name versus generic. We're going to look more at this type of question in a second, but it's actually talking about how long in minutes certain batteries last, and they have the brand name batteries here and the generic batteries over here. And it's saying, hey, just remember, use the old tools we have if you're capable. And one of the oldest tools we learned in this class was just making simple graphic displays of our data. In this case, you can see a side-by-side box and whisker plot where we literally can just look at our data points and kind of compare them just visually instead of doing any type of formal test. Now, if you notice between the two of these, it looks like the generic ones are in general lasting a bit longer, and most of them seem to be falling right here in this IQR range because it looks like there's only one outlier up here above and one below. Now remember, we have two forms of looking for outliers. They're either more than 2 standard deviations away from the middle, or they are outside of the 1.5 times the IQR. Just a little bit of review if you forgot some of that stuff. But down here for the brand name ones, in general, it looks like they are not lasting as long, but there are no outliers here, meaning that it looks like none of their data points fall outside the range qualifications we were just listing there. And it's a little bit prettier of a graph than the generic. But at the same time, it looks like on average, they're lasting a little bit less than the generic ones were. So this, remember, is still useful information to be able to go through, look at a box of whisker plot, and compare the two. But when we want something a little bit more than just comparing to, it's time to move on to using our stronger statistical analysis tools, being our confidence interval and our hypothesis testing. So today we're going to be looking at a two-sample test that will be able to allow us to compare the means of one group to the mean of another. It's very different than comparing the two proportions, but at the same time, it's going to follow almost all the same steps. So even though we're working with different types of data, the process is going to still essentially be the same. And you can see our parameter of interest here, instead of putting just one mu, it's going to have two, where we do the mu of the first sample minus the mu of the second, where this is just the mean and the mean. Now this should be very familiar because the same thing we did when we did the two sample proportions z-test is we took the first p minus the second p, and then again we did this with the two sample z-test where we took the first mean minus the second mean. So none of that should be new. We're going to go through some of the same basics that we've looked at in every video on what does change here. We do have a new formula for our standard deviation or standard error. Remember, it is very rare for us to know the population standard deviation for a situation like this. So we have learned to try to start using the sample standard deviation instead. But along with that, we are unable to use our z distribution, which means that standardized normal curve stuff is not as applicable here. So we have to move on to some new type of test. And that new test is called the two-sample t-interval or the two-sample t-test. Now, again, where does this come from? We covered in the last video where Gossett from the Guinness Beer Company invented a new type of set of distributions that we can use for smaller sample types like this called the t-test. And those t distributions are reliant on something called our degree of freedom, which we'll talk more about in a second. But this new test is going to be almost identical to the old test because, as far as we know, we're going to do everything the same. Our calculator deals with that new distribution curve set. So we'll plug our information into the calculator just like usual. But because we choose the two sample t test instead, it's going to go ahead and use a different calculation to find our final answer. But at the end of the day, we will not be changing our process. Some other things to keep in mind, we do have a new formula for our t-scores when we're looking at the difference between two means. Notice here it says you take the one mean minus the second one. You take the population mean minus the second one, divide it by your standard error using our new formula down here. But if you notice, if you took this as one variable and just made it y bar, and this just mu, and this just y bar, this is the exact same formula that we had for our last t-test. The only difference is we have two samples instead of one, so they went ahead and altered the formulas accordingly. With that said, we can jump right into our assumptions and conditions that are going to go along with this test. Now, just like before, we're going to be testing two major things, your sample size along with the independence checks that we run. None of these are going to be new. We have our randomization condition, which just says we have to make sure the stuff was found randomly. We have the 10% condition, which we almost never check here because it's so rare that with such small sample sizes that we're going to run into an issue of being larger than 10%, but we should still mention it just so that's there. Then we have the nearly normal condition, which we actually looked at with our one sample as well. And this one kind of had some additional guidelines that said, hey, if your sample size is 15 or below, you really should be looking at the histogram or some type of other information to make sure it looks like it's already normal. If it's between a sample size of 15 to 40, then you don't have to worry about that as much, but it shouldn't be out of control crazy. So it should still be unimodal, almost symmetric-ish. But once you get above the 30 to 40 sample size mark, anything past that, it pretty much defaults back to the central limit theorem type stuff, where we don't have to worry about it. We can use it. We're good to go if the sample size is that large. The last type we have here is the independent group assumption, and that's when we simply say that one group happening is not going to change the outcome of our second group. We have already done that as well with our two sample proportion test and our two sample z test. Now, the degree of freedom here is a lot harder. For our one sample, we said the degree of freedom was a rockin' n-1, which was easy peasy. We could find it like that. But with the two sample, you actually follow through this whole thing. Lucky for us, you will never, ever be expected to plug something into this formula. Your calculator handles all of this for you, so don't worry about that. You'll just put in your sample size, and your calculator will handle the degree of freedom that will allow it to choose which t normal curve it will be using. Because remember, the t distribution is a family of curves based on your degree of freedom. It's not just one. So your calculator will do all of this. It'll pick the proper curve to use and do all of that work for you. You don't need to freak out. So let's go ahead and get started with the first type. We have, remember, the two things we're going to look at today. We're going to look at the two sample t interval, which is our confidence interval, and we'll look at the two sample t test, which is our hypothesis test. So starting off, you can see here, nothing should be surprising again. We have right here our general formula for what a confidence interval is. We have our difference of the means plus or minus the critical value times our standard error, where this again is the formula for the standard error, which we saw a few slides before. And this t star, remember, could be found in the calculator by doing inverse t in this case, and it would give us the critical value we'd like. But again, we're not really going to have to worry about that unless it's specifically asked for the critical value, because in this case, our calculator will still do all of that work for us. So with that said, let's go ahead and dive into our first example. All right, so looking at this, a lot of the information for this question is actually missing because they talk about it in the opening paragraph of chapter 23 in your textbook. So you can either go back and read through that and check it out on your own, or I can go ahead and just summarize it for you here by saying that essentially this is a college statistics student that wants to see how much longer a certain type of battery lasts than the name brand battery. So they go out and they buy 6 randomly selected batteries from generic brands, and then they have six randomly selected batteries from the name brands. So then they go ahead and compare them by seeing how long they last by leaving them in like a cassette player or something for a certain number of hours until they die, and they measure how long it takes for that to happen. In this case, we were also given a side by side Boston Whistler plot and a side by side histogram that we can use when we're checking the conditions of this. Now, in this case, they gave us the data as well, like the summary statistics, so we don't have to worry about finding a lot of that. Also, on the first page of the chapter, it did give us the raw data as well, so we could plug those into the list into the calculator and find all of these values on our own. But again, just like if you're taking the AP test, if they give you the summary statistics, do not try to repeat the work of finding those things on your own. It's just a waste of time, and they give them to you for a reason. So in this case, let's look at what we got here. It says, judging from the box plot, and the generic batteries seem to have lasted about 20 minutes longer than the brand name batteries. Before we change our buying habits, what should we expect to happen with the next batteries we buy? How much longer might the generic batteries last? Now, notice this question is not asking us to test the idea of 20 minutes or longer. This question is asking us how long we would expect the difference to be between the generic batteries and the brand name batteries. So, how would we go about giving a prediction for what we believe to be true of the population? This is a confidence interval. So, we're actually going to do a two sample t interval here. Why are we choosing to do a t interval instead of a z? Because we do not have the population standard deviation. In this case, it shows us right here that this is a sample standard deviation. It is the standard deviation we got from the sample of batteries they collected. So we do not have the population standard deviation, which is required for a z interval. So instead, we have to work with our t interval. We know it's two sample because we have two distinct groups here. We have our generic brand batteries and we have our brand name batteries. So that's going to put us in the two sample to t interval. Now, with that said, we do have a list of conditions here, so let's go ahead and check those. Independent groups. Would the batteries of our generic brand change how long the brand name batteries will last? No. One of those will not affect the other, so we don't have to worry about that. That condition is going to be met. Was it chosen randomly? Well, because you're choosing like just taking batteries out of a packet, they're not going to the manufacturing company getting specific batteries that they know came off the line better than the other ones. This is considered to be close enough to a random process. 10%. Is a total of 12 batteries going to be more than 10% of the entire population? Heck no. So 10% condition is going to be easily checked off in this case. The nearly normal. Now, we are looking at sample sizes of 6, which means we do have to be careful. So this little plot of the histograms here is incredibly useful for us for checking off this condition. If we look at both of these, it does look like even though there's such a small amount of data, it is pretty unimodal and does take the whole like high in the middle, low on the sides, which means it's going to be close enough to the normal curve for this to probably be an accurate test to run. Now, if we had a larger sample size, it may help us get more accurate results, but with the data that we have, we'll have to run through. And for the most part, none of these have any serious red flags. Remember, if you do run into something that has a red flag, you can always go ahead and say, I'm unsure of this, but I'll proceed with caution. Now, if that's the case, though, just make sure you're not overusing it because they could deduct points on saying, actually, it did say that it was random in the question. So you're jumping the gun on the whole proceeding with caution problem. Then from here, we are finished with our conditions. So really, we're ready to start plugging into our calculator. Now, we could do the long method of using the whole formula, plugging it all in there, but why would we do something like that when we have everything we need and we have a calculator that can do the work for us? So as always, my class is using the TI Inspire. You can do this same type of work on any type of upper level calculator, if that be a TI-83 or a TI-84. You can just Google how to do confidence intervals for a t-test on there. So again, we're going to go to our menu. We're going to check out statistics, and we have our confidence intervals and stat tests down here. We're going to go to confidence interval. And as I said from the start, we're going to cover all 6 of these. We are finally and officially on our last one, the 2 sample t interval. So we're going to go ahead and click on that guy and see what pops up. First thing it says, is this a data or a stats? We have the stats here, not the original data. We could have plugged in the original data if you read the first paragraph of the chapter, but we have the stats, so let's just make sure we cut all the corners we're capable of cutting without making any illegal moves and put in what we got. So in this case, I'm going to go ahead and make the generic guy R1, and I'm going to make the brand names R2. That way we're all on the same page as to what's what. So if I'm plugging in this data, 206 was the average for that guy with a standard deviation of 10.3, and the sample size for that was a low 6. For our other set of data, it was lasting an average of 187.4 minutes long with a standard deviation of 14.6 minutes and a sample size of 6. Now, what other things does it ask for? It asks for here the confidence level. We weren't given a confidence level to work with, so we're going to leave this as the default 95% confidence. And is our data pooled? We're going to leave this as no, and we're always going to leave it as no, and I'll go ahead and hit back on that at the very end of this video. So we'll go ahead and hit OK, and we'll get all of our data. Notice here that we have a lot of stuff, but that's because we put in information for 2 full samples. So it kind of repeats everything that we put in and also tells us stuff like our margin of error and the difference between the 2 samples. And it goes ahead and gives us the confidence interval we're looking for, which is from 2 to 35 essentially. So let's go ahead and copy that over so we can talk about this in the grand scheme of what's going on here. So I went ahead and just pasted those 2 numbers over here, and let's talk about what this means in terms of our question. So we're looking at these 2 batteries and seeing what the difference in the life of those batteries would be. And remember, this is measured in minutes. So here we can say that based off of our small samples of both of them, we can assume that anytime we buy batteries between the brand name versus the generic, we would expect the generic batteries to last on average anywhere from 2 to 35 minutes longer. Now, obviously, 2 is hardly longer, but 35 is quite a big chunk of time. That's almost a whole half hour you'd be buying for a generic battery. So, again, why is this range so wide? 2 to 35 seems like that's quite a large range of numbers. It's because our sample size is so small. If we had a larger sample size, I'm sure that we would be able to narrow that down quite a bit. But remember, in this case, when we put it in the calculator, we did choose to keep it at the 95. So if we were going to say out loud what this is, we would say, with 95% confidence, we believe that the true mean difference between these 2 batteries types is somewhere between 2 minutes and 35 minutes. So if you're going to go out and buy them, it does look like it's a better choice to choose generic, sometimes just slightly, other times it's going to be quite a big deal. So with that said, let's go ahead and continue on. So that wraps up our confidence interval discussion, and now we're going to move on to hypothesis testing. So again, here's some of the basics that we've shared with every type of testing we've done, all of the formulas and whatnot, but as you can see, a lot of things don't change. Don't let this delta fool you. This is just the change in your information. So delta always kind of stands for the change in. So this is kind of the default, what we've seen for our t-scores. This is the standard error default that we've been dealing with this whole time. So we just need to make sure we remember that as we move on into our hypothesis test. As always, the quickest and best way to jump into this is to actually just go ahead and dive right into a question. So let's do that. It says, if you bought a used camera in good condition from a friend, would you pay the same as if you would buying the same item from a stranger? A researcher at Cornell University wanted to know how friendship might affect simple sales such as this. She randomly divided subgroups into 2 groups and gave each group descriptions of an item that they might want to buy. One group was told to imagine buying it from a friend whom they expected to see again, and the other group was told to imagine buying it from a stranger. Here are the prices they offered for a used camera in good condition. So this is kind of an interesting question. It's actually pretty cool. They're looking at, hey, would people offer more or less money to a friend than they would a stranger that they were buying from online or something? So when you look at the data, you can see they gave us a plethora of information here. We have all of the actual data from the sample over here. We have the side-by-side box and whisker plot right here. We have the side-by-side histogram right here. And we have some of the basic information that they already broke down for us so that we won't have to worry about plugging this into a calculator. Now, the chapter goes through and kind of hits on this a bit more if you're looking at the textbook. So some of this stuff is even expanded further than what you are seeing here. I just grabbed some of the important stuff. So as we know, we're looking at two groups here. So this is obviously a two sample test. All right. And we remember we always should write that out. And I put it right here that this is a two sample t-test. The reason I know it's a t-test is because notice here we do have a standard deviation for each group, but that came from our sample, not for the population. So anytime we have a population standard deviation, we can use that z-test. But when we have the standard deviation of a sample, we have to stick to using our new t-test. So this is a two sample t-test, which means we have these four conditions to keep in mind. Independent groups. She said that she split the two subgroups from the beginning and then asked them individual questions. So that means that one group did not affect the answers of the other group. So we are good with this independent group status. Next off, did she randomly select? It actually does say that she randomly divided the subgroups. So we're going to go yes on the random. Is this small sample going to be less than 10% of the whole population? Yes, by far. There are a lot more people in the world than just these few people that they ask questions to right there. Lastly, the nearly normal condition. This is the only one that would be close to being an eh. I think that this guy right here is enough of a, I don't know, what would you say, a normal model in the sense that it's highest in the middle and then it goes slightly down on either side. This one is a little bit more on the edge. And since we are looking at sample sizes under 15, it would be a bit of concern. So this may be the time when we would jump in right here and say that we will proceed with caution. So make sure you note that, put that in there, let it know. But for the most part, we should be good on this question to continue on. So I'm going to go ahead and get rid of a lot of that stuff so that we can start writing out the rest of the things we would like for this question. Starting off, we do need to have our HO and our HA. And then we already have all of the recorded information that we're going to be putting in the calculator right here. So what would the HO and HA be in this case? Well, in this case, we are dealing with the mean of a group that's asking their friends and the mean group that is being asked to buy it from strangers. Now, it doesn't specifically say in this guy what it wants for us to check if we think it'll be higher or lower. It just says, can you prove that there's a difference between the two? And we said that a common way they go about doing that is by setting it equal to 0, because if there were no difference between the two, that means when you subtract them, it should be 0, because when you subtract one thing minus that same thing, it gives you 0. But down here, we don't have a greater than or less than that's offered here. So this is going to be one of those cases where we do a not equal to for our answer. Now remember, an alternative to writing like this would be to simply say that the one mean is going to be equal to the second mean. And that's how our calculator is going to look at it. And for this one right here, we would stick with the one mean is not equal to our second mean. Now, those two are equivalent to these statements, so don't let that confuse you. You can do either one on the test and you'll be fine. In this case, it does not set a specific alpha for us to work with, so we'll go ahead and use our standard 0.05. So now that we have all of our information, let's go ahead and jump back and forth from our calculator to plug it in. So once we get into our calculator, we can hit menu. We will go to statistics, stat tests, and in this case, we said we are doing a two sample t-test. Again, we want to switch this to stats. Although we had the original data, we did not plug it in here. So let's go ahead and see what we got. First off, looking at the first sample, we have a mean of 281.88. We have a standard deviation of 18.31 and a sample size of 8. And the other sample size over here is 7, just so I don't have to keep flipping back and forth. It looks like then from there we got a mean of 211.43 and a standard deviation over there of 46.43. And as we scroll down, we can see here, we actually do want the not equal to. And again, I said we're going to leave the pooled as no. So when we go ahead and hit that, we find out that we have all of our information here. Degree of freedom in that crazy formula turned out being 7.62305. But here's what we really want is the p-value. So I'm going to go ahead and copy that guy and pull it over here. Let's see, pull that guy down. And this again was our p-val. So looking at this p-val, it is 0.005, whereas this is 0.05. So the alpha was 5%, where this is 0.5 of a percent, almost 0.6 of a percent. So this is obviously less than alpha. And when we are less than alpha, we get to reject that hoe. So that means that we can go ahead and reject the null hypothesis, and we can move on to accept our alternative, that these two are not the same thing. So at the end of the day, how would I write a sentence for this? I would say something along the lines of, after looking at this information, there is enough evidence to reject the fact that someone would offer the same amount of money to a friend as opposed to a stranger. And in fact, we can accept that that would be a different value for the two groups, or something along those lines. Obviously, you can word that in a much more elegant way, but as long as you are expressing the fact that you rejected the fact that they're the same and you have accepted the fact that they are different. And remember, because we have already listed our test, already listed our conditions, already have listed our null and alternative, what our calculator gave us, all the information we plugged in, and our alpha, it should be very clear to the reader why we chose to reject and accept the alternative. You don't need to write out all of that information in your final because it's all there. Just make sure that you don't cut corners and forget to write any of this information down. Now, as promised about the pooled little snippet in the calculator. Remember, in proportions, we were able to deal with pooled because we were able to use a formula to talk about what we believed the population standard deviation to be. And in a null hypothesis, when we assume the two to be the same, that means they have the same standard deviation, so we were able to pool the data. That means that technically we could do the same in this case, but we would have to be able to to assume that the variances or the standard deviations of the two groups are the same, which, since we don't know a population standard deviation, that is near impossible. And remember, it's never required to pool information together to run the test. A lot of times it's actually better to keep them divided. So when we are working with something like this, you never should pool them. Now, do some statisticians do them in the real world? Possibly yes, but again, you can see over and over here with an AP textbook, it says it's never wrong to not pool. You should never do it with a t-test. So just don't. Like, there's no reason to jump into that. We can't really guarantee that these standard deviations are going to be equal. So with that said, anytime it pops up in the calculator for a t-test on if you want to pool it or not, the answer should always be no.
Well, guys, that's actually going to end our discussion on hypothesis testing and confidence intervals. At this point, we have gone through all 6 types that our calculator offers. We've done the 1 sample z-test, the 1 sample t-test, the 2 sample z-test, the 2 sample t-test, the 1 sample proportion z-test, and the 2 sample proportion z-test. So there is a total of 6. We have gone through all 6 of them. If you want to go back and check out any of the previous videos on this, you can always find them on my YouTube channel at MrCaproni, no space, no period. And you can look back, see all the different types, see how we used them, when we used them. I'm going to try my best to create a one-pager so you guys can kind of reference that pretty quickly and see which ones are used in what situations and what are the differences between them. But in general, it's the same process every time. For a confidence interval, you always have whatever statistic we're looking at, plus or minus the either t or z value, critical value, multiplied by your standard error. That's always our confidence interval. For the hypothesis testing, we always follow our 7 steps. We pick our test, we check the conditions, we go about listing out all of our information, we go about plugging it into the calculator, getting our p-value. Once we get our p-value, we compare it to our level of significance, the alpha. Then we either reject or fail to reject, and we write a conclusion. I know it's been a long process, and we've gone through a bunch of different types to use here, but the safe thing is that all of these processes are the same. So you keep doing the same thing, it's just a matter of picking which test to use. So I hope you guys found something helpful in this video and the videos before it, learned something new. And as always, guys, stay fit, stay healthy, and have a wonderful day.